in the tables. Just leave it outside for it to just get out. We love this thing. And thanks also for filling out the very brief in-class feedback. It's always good to get a sense of how fast we're going and whether or not we're losing you in this sort of whirlpool of ideas. We're going to talk today about the stock market. We're going to talk about crazes and crashes and correlated events. And we're going to talk about how people make inferences based on things and how those inferences go wrong. We're going to talk about this gentleman here. His name is Gordon Gekko. But before I do, I will just walk us through these two problems. So, in the first case, in the first one, we have something you don't know. The thing you don't know is whether or not your coin is of type 1 or type 2. If the coin is of type 1, the probability of heads is 1/2. If the coin is of type 2, it's one of these biased trick coins that never actually exists in the real world, and it comes up heads 3/4 of the time when you toss it. So you don't know which coin you've been given, and you toss it 3 times, and you get 3 heads in a row. So the question this problem poses is, given the data that you've gotten, given what you've seen happening in the world, what ought you to believe about the nature of your coin? And you're given a sort of space, a theory space, a set of ideas about what the coin might be. Right? These are not the only 2 kinds of coins that could exist in the world, but we're going to say that you're choosing between these 2 possibilities. So the first thing, as a Bayesian, you think about is, well, I never come in without beliefs. I never come in with no idea what's going on. If I think I have no idea, then at least I know that I have no idea. What we're going to do is say that you have a general belief that the coins you encounter in the world are pretty fair. And so the probability that you've been handed one of those trick coins, or your degree of belief that you've been handed one of these trick coins, is 0.2. Okay? So you come in with these beliefs, probably the coin is fair, 80% level of belief that the coin is fair, and then you get to play with it. You play with the coin 3 times, and you toss it 3 times. Okay? So what ought you to believe, in particular, what ought you to believe about the coin, given that you've gotten heads 3 times in a row? What's the degree of belief you have in the coin being of type 1, let's say, given that data? So you do the magic trick here, use Bayes' theorem to turn a question you can't ask into a question that you can. Let's see how good my formatting skills are at the edge of the board. This is what you want to know, the probability that the coin is of type 1 given the data. But this is what you can write down, or this is what you can calculate. This first term here is the probability of getting 3 heads in a row if the coin is indeed fair. This term here is what we call that prior, the degree of belief that you have that the coin was fair coming in. And then you have this normalization factor. The normalization factor is just the sum of that first term here, the probability of getting 3 heads given that it was a coin of type 1, plus the probability of getting 3 heads given that it was a coin of type 2, each of them weighted by the prior. So to answer this question, all you have to do is plug in each of these terms. The probability of getting a coin, or getting 3 heads in a row with a fair coin, is just 1/2 times 1/2 times 1/2 equal to 1/8. The probability of getting 3 heads in a row with a coin of type 2 is 3/4 times 3/4 times 3/4, or cubed. If you did this, you might have typed it into your calculator. You can also just write it as a fraction. So now we have everything we need to calculate what you ought to believe. We know this term here is 1/8. We know this term here is 0.8. We have another 1/8 times 0.8. And we have a 27/64 times 0.2. You plug all that in, and here's what I calculated earlier. 0.54. One way to reason through this problem is that what it's telling you is that even though you get evidence for this kind of coin, the evidence is not sufficiently strong to overweigh your priors. It's more likely to get 3 heads in a row if the coin's biased towards heads, fine, right? But your prior belief that that kind of thing goes on a regular basis is pretty low. So even though you've gotten data that tend to favor the second hypothesis, that second hypothesis you think is sufficiently unlikely, in fact, that you walk out the other side thinking the coin is still just slightly more likely to be a fair coin than it is to be biased. Any questions? All right. The second problem will lead us right into our class today and into the repeated disasters of the American stock market. So in this case here, you have 2 coins. We have our type 1 coin again. It's fair, right? So P heads is 1/2. And now we have this type 3 coin. And the type 3 coin is a coin I guarantee you've never seen before. The type 3 coin, the probability of heads when you first toss it is 1/2, but the probability of heads, given that you've just gotten heads already, is set to 0.9. So now we get data. I give you this coin. We don't know if it's type 1 or type 3. I give you this coin, and just to make it fun, let's toss it 5 times. So you get heads 5 times in a row. So, what ought you to believe, and in particular the problem asks you, what degree of belief should you have that the coin is one of these crazy cascading coins, that once you get a head, it gets more likely to get the next head, right? You might think of this coin if you're, like, I don't know, following basketball. This is the hot hand effect. You score a basket, like, whoa, hot hand, I'm going to get more baskets, okay? This is like the least interesting hot hand effect ever. It's a coin tossing hot hand, I'm sorry, okay? Also, this is the last coin tossing problem you will ever see in this class, I swear. The reason we toss coins is because the Reverend Bayes tossed coins early in his life, and I guess he never got over it. All right, so let's flip this around. You guys are Bayes experts. I don't even have to slow down to write H 5 times. I'll just write it like this, okay? I told you that you don't have to worry about it being a coin of type 2. We're just going to focus on these two interesting cases. So again, we've invoked Bayes' rule. You don't know how to answer this straight away, but you do know how to calculate each of these things here. I asked you again to put priors that were the same as before. Your degree of belief that the coin is a normal coin, that the coin is like a basketball player without a hot hand, is 0.8, and your degree of belief that this is like the Michael Jordan of coins is 0.2. So we just have to work out each of these terms. Well, you know how to work out this term here already. The probability of getting heads 5 times in a row if the coin's unbiased. That's just 1/2 to the power of 5. You know that guy there. That's 0.8. You know this guy here. That's 0.2. And now all you have to do is figure out how to compute this thing here. What's the probability of getting heads 5 times in a row if, once you get heads, it's more likely to get heads again? Well, probability of getting the first head for a coin of type 3, well, that's just a fair coin toss. He starts out, it doesn't really know it's about to be tossed. Okay. Then the probability of getting the second head is now higher because you've already gotten a head. Okay, that happens half the time. This second head happens a lot more often because it got sort of triggered by that first head. That's our little coin story. And in fact, that's 0.9. And then the next head follows on from that one. Again, this guy here, this toss is more likely to come up heads because of the previous toss. You can see where this is going. And out the other side, once you do all these calculations, you get, hang on, 0.33 for the term here. In fact, it's remarkably likely that you get heads 5 times in a row if it's one of these biased coins, right? Once you get that first head, it gets a lot easier to keep the run going. That's our magical biased stock market coin. And if you plug all these terms in, I won't make you watch me scribble this out on the board, it turns out that even though you think the chance that you've gotten one of these coins is pretty unlikely, it turns out that despite your skepticism, after seeing 5 heads in a row, your degree of belief that the coin is unbiased is about 0.72. So that first question follows on pretty reasonably from what you've seen in the previous lectures and in the handout. This one here, it's a little bit more of an adventure into the more complex kinds of effects we see in the real world. Nobody is an unbiased coin, and nobody is even a coin that forgets what's happened before. In general, what we do in our lives, what we see around us, depends upon the things that have already happened. It rained yesterday, that makes it more likely that it's going to rain today. Sometimes we say that there's memory in the system. The reason we love coins is that they're theoretically without memory, but most of the things we care about happen. All right, one thing that struck me, I have brought my cell phone here today, like some of you, which is just fine. If you're on it all the time, maybe don't come, but that's cool. If you would like to ask a question, but you're like kind of nervous, you can text me and it will ding. So I've done this when I've had very large classes. So if I hear a ding, I will drop everything and I will make fun of your area code. No, I won't. And I will not even know who you are, okay? So you can do this anonymously. I have dressed up today as Gordon Gekko. This is Gordon Gekko. He was a man in a movie in 1984. This is actually Michael Douglas playing the character Gordon Gekko, who was based off of the kind of guy you tended to encounter in Wall Street in the 1980s. Michael Douglas, Gordon Gekko, is somebody who played a great deal on the ways in which people spotted patterns in the world and drew inferences on those patterns. Gekko's character is somebody who stays one step ahead of the game. We talk in this class on a lot of different levels. We do some really nerdy math behind this. But it's also worth noting that Gordon Gekko, the stories that we tell actually tend to become reality. It turns out that this movie, Michael Douglas's character, was so compelling to people that people on Wall Street, people who dealt in stocks and bonds and traded, started imitating him. The line famously in the movie is "Greed is good." So, people are like, you're terrible, you're just screwing people, you're just taking all the money for it. Greed is good. So this was his tagline. And it so turns out that even 20, 25 years later, people are still modeling their behavior, modeling the kind of person they are, based on an entirely fictional story. In late 1987, Frank, then a math student at University of Kansas, had an epiphany as he sat in a cinema watching Wall Street. I was naive, but it actually inspired me. It made Wall Street seem exotic and alluring. The movie became a hit, and instead of simply reporting on the way things were, instead of telling a story about what was happening on Wall Street, it actually ended up being a story that other people drew on in their real-world activities. Stories matter. Myths matter. It's one of the reasons that we had myths in the past. We are not beyond the myth-making era. We have myths now. Another example of how film creates reality is not the movie Wall Street, but the movie The Godfather. Has anybody seen The Godfather? Okay. It's a movie about the mafia. It was made in the 1970s. It's one of these very violent, hard-edged films. It started an entire genre of mafia movies. This is Al Pacino in The Godfather, actually, in the second episode, the second version of the movie that came out, the sequel that came out. One of the things that the FBI realized was that people who were actually in the mafia were watching The Godfather and copying. So, for example, in The Godfather, one of the things that happens, this was just made up, one of the things that happens is that the way the different members of this crime syndicate greet each other and show respect is they kiss the other person's hand as a sign of respect. This is just made up. And the FBI started noticing that actually mobsters, when they were tracking them, were doing this. Even worse, it turns out that the phrase "The Godfather" is not really a commonly used phrase in the mafia world. It was famous in the movies, and in fact, now, when they were wiretapping people who were, in fact, in the real-world version of the mafia, when they were wiretapping people, they found that people were actually calling, saying, oh, the godfather of this other family. So once again, right, we often are much less interesting than we seem, and we often ask people to tell us how to behave. Okay, so I promised you no coin tossing. We're going to do, instead, Gordon Gekko, we're going to do Wall Street. And I'm going to do some statistics now, do a little Bayesian analysis of the stock market. So I pulled, just for the sake of argument, the stock prices for Apple Computer, some of which you may own, or rather some of the goods of whom you may own. Very simple. How do you get the stock market data? How do you get the prices of Apple stock on every single day? Well, you just type it into Google. And it gets this web page here, and then you can download a spreadsheet. And this spreadsheet starts at the very first day that the market was open for Apple, the very first day it went on the market. And it will tell you the date, it will tell you the price at which it opened. So you could have bought Apple stock for 51 cents in 1980. It opened at 51 cents, and in fact, it closed almost exactly at the same price. The next day, okay, on the first day, it closed at 51 cents. On the next day, it opened at 48 cents. So in fact, on day 2, the stock was worth less than it was on day 1. And on day 3, okay, the previous day it closed at 48.6 cents, or sorry, at $0.486, 48.6 cents, and it opened at 45.3 cents. So again, it went down. You can do this over and over again by machine. And now we get a very expensive set of coin tosses. So this is the first day, or rather the second day, of selling stock on the stock market for Apple. On that first day, the stock went down. On the next day, it went down. On the next day, it went up. The next day, it went down, 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 up, down, down, up, down, down, up, down, up, down. I won't do it all. There's 9,000 of them, right? But this is the pattern. This is the signal that the market was sending all of us. When you look at this, has anybody here tried to invest in the stock market? Okay. Well, I guess that's how you're paying for your education. There are people they're called chartists. Somebody who's a chartist is somebody who decides on whether or not to invest in a stock based upon the movements the stock has made in the past. They're called chartists because it's like you look at the chart, so I'm a chartist, right? And so you look at this and, even I'm, it's just sort of tempted to do things like this. Like, check it out. Like, there are all these runs here, these rallies, right? Like, it went up 5 days in a row. It went up, like, 10 days in a row, 4 days in a row. Of course, you could look at the other side, too. You can look at the other side, too. It looks like there was a run of downs here, right? Then it kind of oscillated a little bit, right? Then there was another run of downs, another run of downs. Oh, but then maybe there's some more ups and some more ups and some downs back and forth, right? Is there a pattern here? Is Apple a coin that's just getting tossed every day? Does the market wake up and look at Apple Computer and say, not worth as much as I thought, or worth more than I thought? Well, so let's go into this, right? We can take this data stream. This is just like heads and tails, except now it's ups and downs. We have 9,517 days of trading on Apple as of this morning. The number of up days that Apple had, the number of days that it ended higher than it finished the day before, is 4,682. For a grand total of the probability of up being 0.4919. An almost perfectly unbiased coin. Probability of down, as it must necessarily be, there's only 2 things the stock can do, go up or go down. If it at exactly the same price, I said it went down just for argument's sake. Right? So the sum of these 2 here, of course, must equal 1. So what do we do with this? Well, one thing is you can take the problem 2 that you just worked out and say, okay, look, if Apple had an up day, what's the probability that the next day Apple would also be up? Is it like that coin that, once it got heads once, be heads next another time? Is there such a thing as a stock market rally? do people start saying, whoa, Apple is good, it went up yesterday, and it's probably going to go up today. So what we can do is we can count all the times that we see a U followed by another U, right? 2,341 times. Just run that through your spreadsheet. And you can divide by the number of times you get a U followed by anything. So take this number here and divide by this number here, and what you get is the probability of having an update, given that you've just had an update, is 0.500. It turns out it's not precisely 1/2, but it's close enough. This is not the world's most correlated coin, right? The coin that you played with, you toss it the first time, it's 50-50 heads or tails, but if you get a head, it's 90% heads the next time. In this case here, there is at best an incredibly weak effect. It is true that if you get an update, it's slightly more likely that you'll get another update by 1%. 1 percentage point more likely that in fact it will go up the next day. We can of course also look the other direction. We can say if it goes down one day, is it more likely to go down the next day? You do the same calculation, and in fact, it turns out that, yeah, there's a little bit of an effect, right? The chance of an update just at random is 51%. The chance of a down day, given that there just was a down day, is, okay, 52%. So very weak effects, but they are there. Aha! Okay, not in this class. So where does this bias come from? This is actually kind of a problem. The ability to even just barely predict what's going to happen next with Apple, right, is a problem for a lot of people. And here's where the problem comes from, right? So if you can predict that Apple today, because it had an update, will have another update, if you know what's going to happen in the future, you can make a whole bunch of trades. You can, essentially, the stock market allows you to bet that tomorrow it's going to go up. When you place those bets, you drive the price of Apple today upwards. The more of those bets you place, the more people place those bets, the less likely it is, in fact, that you will have an update. You drive the price up today by inputting information you believe about the future. This is a phenomenon that we see quite a bit. If, in fact, I really could predict, even at the 1 percentage point level, what Apple's going to do tomorrow, I would never have to work again. That's an incredibly good level of predictive power. And one of the reasons we believe that is this precise phenomenon. It's the old joke that the economists say. There's two economists walking down the street, and they see a $100 bill lying on the ground. And one of the guys reaches to pick it up, and the other says, no, 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 don't bother. If it was real, somebody would have picked it up already. Aha. Okay, definitely not in my class. Okay. This is called the efficient markets hypothesis. A fancy way to say it is prices contain all of the available information about patterns in them. There are no undervalued stocks. If you know Apple will go up tomorrow, you could just buy some Apple today and drive it up today. Traders are no fools, is another way to put it. If there is a predictive signal, they should be using it. So obviously this clashes with a great deal of research that people do. This is a paper by a colleague of mine. Twitter mood predicts the stock market. These kinds of things that we do, the ways in which we look for patterns, is in conflict with a basic story that we like to tell about the financial markets. That in fact the financial markets know everything, or at least as close to everything as they might know. All right, so let's dig a little deeper here. Let's just say that the efficient markets hypothesis is not true. I promise you it's not true, but it doesn't stop people saying it's true. Let me just go here and consider these patterns. Okay? And in fact, what I'm going to do now is I'm going to measure these patterns over time. So notice, for example, that the probability of up given up is a little bit higher. Instead, what I'm going to do now is I'm going to plot this over time. And in particular, what I'm going to do is plot the probability that Apple has an update, given that it's already had an update, divided by the probability that Apple has an update. So when this is greater than 1, it means that there's a hot hand for Apple. It means that up tends to be followed by up. If it's below, it actually is the opposite. It means that up tends to be followed by down, more likely. than on average. You can think of this as the sort of rally dynamics. It's positive feedback. If Apple goes up, somehow people are acting in such a way that they make Apple go up the next day. On the bottom half here, this is negative feedback. So if Apple goes up, they're like, whoa, 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 whoa. Not sure about that. And they buy and sell in such a way that Apple goes back down the day. So the dotted line is the same. Right? The solid line is the up rally line. Probability of up given up. The dashed line here is the probability of down given down. So this is the opposite one. This is dump it, okay? So again, when this dashed line is above 1, that means that if Apple's had a down day, people are more likely to buy and sell in such a way that they make it go down again. Okay. So, and interestingly, year 1, 1980, we only have a little bit of data for year 1, but in 1980, the probability of down, if the stock just went down, is about twice the probability of down on its own. Whoever was buying and selling Apple in its early days was very easy to spook. If it went down, right, or the group of people who were buying and selling, if it went down one day, they were twice as likely to do stuff that make it go down the day after. So that's actually an opposite page. It settles down more to sort of 10s or 20 percentage points. So, one way to tell this story, one way to tell a story about these correlations is the following, right? People aren't just putting information into the market. They're not saying, oh, man, great product, I'm going to buy some Apple stock. Right? Or, man, they lost a great CEO, we're going to sell off. Instead, people are actually using the market itself as a source of information. These are the chartists. These are the people who don't know about the companies that they're buying. And all they do is look at the fluctuations in the stock price and decide what to do next. We have data, actually, from a company called TD Ameritrade. TD Ameritrade is a sort of the discount broker, so people often go there who are not experts in trading on the market. And people are chartists all the time. In particular, for example, if they buy a stock at some time and it goes up, they're more likely to buy again. This turns out to be mildly irrational behavior. So what's happening here? What's happening when we're above, in this red zone here, of positive feedback? Well, one way you can tell a little story of some person sitting in their office, and it's like, well, I don't know what Apple's going to do. What the hell do I know? Right? So what I'm going to do is, I'm going to just watch other people. I'm going to see what they're going to do. And then I guess I'll do that. Right? Like, what could possibly go wrong? Obviously, when this person goes through this chain of reasoning, they're stuffing information here so that other people like that guy are going to have a greater signal to do what's already come before. So another way to say this is, when you're in this regime here, you're potentially in the regime where people don't know a lot, and they're watching the stock price. And if the stock price goes up, they say, well, at least other people think it's worth buying. So, what are these points? You can see that this market here goes in the red and in the blue. This is the kind of conservative feedback. In some sense here, what people are doing is saying, well, it went up, but I have a sense that maybe there's a true price of this commodity, and so it went up and I'm not going to buy anymore. They drive the price down. But what's happening when they're in this phase here? Well, the most obvious thing is at the beginning there's a lot of positive feedback. And one reason to say that is nobody had any idea what the hell Apple Computer was. Apple was building a personal computer. No one really knew what a personal computer was at that time. Our understanding of what computers were was mostly driven by the idea of a mainframe, something sitting in a big university like CMU. Nobody knew what this was. And so one way to explain why you had all this positive feedback in either direction was that people didn't know, and so they just looked at the market. They said, I don't even know what they're selling. Okay? And so I'm just going to watch what other people do, and in particular, I'm going to go watch what the market does. All right, here's the next excursion into this positive feedback dynamics. It's essentially something in Christmas of 1989, around this point, where Apple had in fact been doing extremely well for the previous 10 years, but it hit a big rock. They weren't able to sell computers, they didn't meet their stock market targets, or they didn't meet the targets that they had promised their investors, that they had anticipated, and all of a sudden nobody knew what to do. And that's borne out, potentially here, in the fact that people all of a sudden are now watching the market again to decide what to do. An update's followed by another update. Here's the next moment when it has the positive excursion. This is an interesting one. If you remember the guy Steve Jobs, Jobs was, of course, one of the founders of Apple, along with Steve Wozniak. Wozniak went off and just did science, had a good time. Jobs stayed and ran Apple for many, many years. At some point in time, he got forced out. But in 1997, he was brought back. And nobody actually knew what it meant for Jobs to come back. Again, you see it reflected here. People are making decisions on whether or not to buy and sell Apple, in part correlated with the decisions that people made the day before. And we'll do one more positive excursion, significant one here in 2010, actually between 2009 and 2012, which is when Steve Jobs was diagnosed with cancer and became sick and no longer could run the company. Another point of uncertainty. And so what we're seeing here, in fact, is that people appear to be turning towards the market, or at the very least, are leading to market rallies and market sell-offs in conditions where they don't necessarily know exactly what's going to happen. Down here in these periods, people have stronger theories about what's going on. When they're up here, they have weaker ideas and turn to the very source of information that they're themselves troubling. Right? They're looking at which way the water is going by waving their hand. Of course, it changes the way the water goes. So, there is a feedback effect, at least a weak one in Apple. It doesn't necessarily mean that things will go through the roof, right? Just because the chance of getting an up day conditional on having an up day is slightly higher than just the baseline condition, it doesn't mean that, once Apple has an update, it'll just go out of control. Hot hands end, or at least they usually do. They become harder and harder to end, but if you keep rolling the dice, eventually they will. So even in this case here, where you have, let's say, a 10% bias conditional on the previous day, you're not going to get much. You can look at Apple, you can say, okay, look, what's the probability of an up day given an up day? You know that, it turns out to be 0.49, or sorry, 0.5. The baseline is 0.49. What's the probability of an up day given 2 up days in the past? Okay, just barely higher. It fluctuates around here, but there doesn't seem to be some kind of effect that kicks in where if you have, let's say, 7 up days in a row, you're guaranteed at a very high rate to get another one. There don't seem to be these arbitrarily driven runs on the stock in either direction. There's an effect, but it's weak. So these kinds of effects are not always weak, and this is the problem. So I'll tell a story about something called the flash crash. This happened about 8 years ago in 2010. The flash crash was driven essentially by a set, it turns out, of machines, not humans, making predictions about the world based on what they're seeing, taking actions based on those predictions, altering the world in response, and providing a new source of information for other players in the market. What happened is what always happens in these positive feedback effects, is that the thing that caused people to do X, right, is intensified by the very act of people doing X. The thing tells me to do something, I do it, and it tells me a stronger signal to keep doing it. Okay? So the flash crash the stock market lost 9% of its value in 20 minutes. This happened incredibly fast. 20 minutes is a short period of time, even in the stock market. 9% is a very large drop. Your grandparents or great-grandparents may remember the crash of 1929, the Great Depression. This is probably the world's worst market failure we've had in the United States, in the 20th century at least. We wait to see what happens next. Here's the crash. Here's the price of the Dow Jones of the stock market at the time. And you can see it's kind of going along 1928, early 1929, and then something falls off a cliff somewhere around October. Right? The price drops from here all the way down to here. The amount of value it lost in a few months, I'm going to overlay the amount of value that the flash crash lost, is, hang on, just about there. So the event that essentially crashed the American economy for 10 years took a few months. The flash crash, a big chunk of that apparently happened in 20 minutes. So what happened? Right? I'm going to play you, fortunately, we have now great video and audio of, Gordon Gekko types screaming at each other. Here's the stock market price, and that's the flash crash. And again, this is happening on sort of time scales of 5 or 10 minutes. right? This is the Wall Street crash, the beginning of the Great Depression in 1929, and this is on the order of a month or so. Okay? So here it is. This is live audio, and overlaid on that is, at the same time, the price graphs that all the people were seeing as they were buying and selling on May 26, 2010. So,
53. Once again, 80 minutes trade, 90, 80 the minute or even here, guys. Once again, 80 the minute or even. That's a 90, 80 the bid. 98s are trading here now. 97 halves are trading here now. Once again, 97 units are trading here, guys. 96 halves trade. 96 evens trade. 94 units are trading. 94 evens are trading here now, guys. Once again, 4 half offer, 4 even offer, 3 halves do trade. 93 evens are trading, 92 evens are trading here now, guys. 91 evens are trading. 89s are trading. 88 halves are trading. 87 evens are trading. 86 evens are trading. 85 evens are trading here now, guys. All the way down. 84 evens are trading here now, guys. 82 evens are trading. Paper comes in a big seller. 81 evens are trading here now. There's 79s are trading. We got 79s trading here now. Once again, 78s are trading. 6s are trading. 76 evens are trading here now, guys. 75 evens are trading. 4 evens. 3 evens are trading here. 2 evens are trading. 72 evens just traded. Once again, guys, we are big time evens in here now, guys. 72 even offer. 68 evens are trading. Guys, 70 evens in here now.
all right. So, and from his point of view, from the point of view, I don't know why this guy doesn't take time to text his family. Because from his point of view, the entire market, trillions of dollars are now disappearing from the stock market before his eyes. And if you hear in the background, everybody else sees the same thing. Yes, question?
So what happened? I really don't know anything on stock market.
Yes.
So what happens? So that happened.
Yes.
He's freaking out.
He's freaking out.
I don't know what he's saying.
Okay, yes, no one does. No one does.
So that's like 1 minute.
Yep, that's like 1 minute, yeah.
So then what happened after? Why is it going back up like so fast?
We'll get there.
Okay.
We'll get there. But it's a good question. Let me just sort of, it's, what's the stock market? I have no idea. No one really knows what the stock market is. But you can think of a stock as something you can buy, and it's got some price, right? It's like a car, except the only problem with a stock is you can't drive it anywhere, okay? So what the guy's yelling out is he's just yelling out the price at which you can buy some object. I think he's selling bonds here. I'm not quite sure, right? He's yelling out the price at which you can buy something. And what this is tracking here on very, very fast time scales is the price, in this case, an average price of all of the stocks, all the significant stocks in the market. So at 8:30 in the morning, the average price is 1,160 units, right? And then by the end of his screaming, it's dropped about 10%, okay? So here we are. That's where the audio is taken from, okay? You can see a couple things in this graph. So fortunately, yes, right? Indeed, it did bounce right back up, and we'll talk about why it bounced right back up in a second. One of the things that you can see is sort of fun. Notice the jitter here, right? You notice how there's fluctuation that's moving around, right? And there's sort of a kind of a standard fluctuation from minute to minute, right? So, its average is like this. It kind of moves a little up and a little down. Notice that even after this crash has happened, even after everybody's panicked, right, this jitter is much higher here. So somehow, even though it's recovered, people are now moving the price a much wider range than they did before. Yes, question?
Okay, so this happened in 2010, but then something even worse happened in 2008, right?
Yeah.
So that was like an actual stock market crash, and then this was a flash.
Yeah, it's called a flash crash just because it happened quickly. And as we'll see, they actually...
But then they recovered.
Well, they actually just hit undo. Like, everybody agreed that it didn't happen.
So everybody thought it did?
We'll get there. Yeah. This is weird. It's weird. This happens like once every 10 years, and it's probably going to happen more and more often, right? So, just to say where we are, right? So, what happened is, all of a sudden, the price started dropping, right? It hit some bottom here, okay? In fact, everything got so crazy at this point that some people could buy Amazon for $0, and other people could sell Office Depot for $10,000 a share. I mean, the entire system broke, the ways in which trades were made, and it broke in part because the machines weren't built for these kinds of deviations, okay? So let's talk about why this happened. So, okay, let's look. So the crash starts somewhere around 2:30 p.m. At the same time that that's happening, okay, 2:30 p.m. New York time is about 8:30 p.m. in Athens in Greece, okay? In Greece, at the time, this is after the 2008 crash, which was a real crash, and nobody hit undo on that crash, or rather, all the wealthy people got to hit undo, but everybody else, none of those guys got to hit undo, okay? And one of the signs that no one else got to hit undo is all the countries in Europe all of a sudden had to roll back their spending, right? They had to cut finances, they had to cut services for hospitals, they had to cut school teachers, they had to cut university funding, and in Athens, it just so happened, they called this austerity. You have to be austere about your spending, that's what the countries were told. And this triggered riots, and in fact, around 8:30 p.m. in the evening in Athens, in Greece, a bunch of students started throwing bricks at cars and overturning buses and setting them on fire, and this turned into the whole thing that happened. So these two things happened roughly at the same time, and one of them is probably associated with the other. No one is quite sure exactly how this all happened. Of course, nobody really wants anybody to know, because if anyone figured out whose fault it was, then they'd be in a lot of trouble. But we're pretty sure the following sequence of events happened. Okay, so first of all, it was a bad month already, okay, in 2010, in that May, right, or just before. People were worried about their portfolios. People thought the market was not going to do so well, okay. That second thing, that riot in Greece, was part of a long-term process of Europe slowly coming to terms with the financial disaster, and in fact, all of the financial decisions that the elites had made bubbling down to the ordinary person. And the ordinary person in Europe was very mad, okay? And they started setting things on fire. And one of the concerns that governments had, at least wealthy governments had, was all the countries that had their people setting things on fire maybe wouldn't pay some of their debts, and so this started to worry them even more, okay? So the market is weak, and these riots start. And at 2:32 p.m., perhaps as he's watching the television, a money manager, a guy who runs something called a hedge fund, right, which is essentially a big sort of bundle of stocks that you can buy together. So you go to the hedge fund, you give them $10, and they split up your $10 amongst a whole bunch of stocks for you. Okay? So this hedge fund guy decides that he's going to sell some of his shares, okay? He's worried about the market, and he wants to get out of the market and move into a different part of it. He doesn't want to own the particular kinds of companies that he already has, okay? So how many shares does he want to sell? He wants to sell $4 billion worth of shares, which is about 3 times our endowment at CMU, okay? Now, the other problem is he did it by computer, and we'll see exactly why this was a problem, right? So this guy is going to be discreet. He's not just going to sell $4 billion worth of shares all at the same time, right? If you tried to sell $4 billion worth of used cars on Craigslist in Pittsburgh, the price of used cars would go through the floor, right? You could get one for $1. He didn't want to flood the market with a whole bunch of the same thing at the same time because he was worried that the price would go down. So what he did was he did something, technical term, won't be on the quiz. We don't have quizzes, but won't be on the quiz, right? Technical term. He did what's called a liquidity-driven trade. So what this means is he told his computer, okay, I've got $4 billion worth of stocks to sell. Don't tell anybody. Like, sell a little bit, wait till it gets bought. Just kind of watch how much people are trading that stock, and just kind of, as that stock is getting traded back and forth, just kind of parcel more and more out, right? This is called a liquidity-driven trade. So, here's his computer, here's his hedge fund, right? And so his computer's hooked into the stock market, and it's slowly selling some of these stocks, right? So, some of this gets sold to your grandmother, okay? And on the other hand, some of it also gets sold to other people who happen to have computers, right? And in fact, a lot of these computers start buying them, okay? So as this happens, right, as this hedge fund is selling stocks, and this guy's happy, the computer's like, I'm, doing well, right? No need to worry. As this one's selling it, the computers are buying it, but then the other computers start trading the stocks amongst themselves, okay? So not only have they purchased from this machine here, but this machine starts purchasing the same stocks from this one, and this one actually starts purchasing them back and forth. These machines all start trading amongst each other. And this happens very fast. It happens on the timescale of milliseconds, so thousandths of a second. So first question is why? Who are these machines? Why are they buying stocks and then selling them right away to another machine that just sells them right away to somebody else? Why are all these trades happening? Sure, I get this machine might say I want some of that stock and buy it, but why does it immediately sell it and then even buy it back? What's going on? These are people that we've come to call high-frequency traders. So the people who own these machines go by this name here. So what is high-frequency trading? High-frequency trading is what you might get hired to do out of Carnegie Mellon University. It says basically find patterns in the stock market as quickly as you can and trade on them before they go away. Right? So we found a pattern for you this morning, or rather this afternoon. You don't have to pay us, it's free. Okay? And the pattern was that the probability of an update given a previous update was slightly higher than the baseline. So if you see an update, quickly buy it because it's going to go up. Right? I would not recommend using this, in part because, of course, the time scale of that pattern is like day to day. Okay? Instead, what these machines do is they have like some machine learning. They're finding patterns and saying, okay, if these set of things happen over here, then this thing will happen over here. And okay, you have maybe a few milliseconds to make that trade before the prices go in the wrong direction. So these machines say, oh, pattern, quick sell, right? Somebody else buys it, okay, they make a profit, right? Turns out this is actually a way to make money. Here's an example. So on this graph here, the blue and the green, these are two objects you can buy on the stock market. They are essentially the same thing. In fact, by definition, they're the same thing. So these prices should move up and down precisely at the same rate. I've just moved these, right? I've just shifted them one from the other, right? So these should, and in fact, this is like 1 minute. This is 1 minute tick, tick, tick. You can see they do, in fact, exactly match each other. But if you zoom in to, a quarter of a second time scale, you can see, in fact, that this one goes up, right, before this one does. So if you quickly buy this one, right, you can sell it on this market over here and make some money. You need a really fast machine to do that. In fact, not only do you need a really fast machine, you actually need to have like a really good connection to the stock market itself, right? Because this is happening almost at the speed of light. So you can't just call somebody up and make the trade. By the time you've dialed the phone number, the possibility to make the money is over. And in fact, what these guys have done now is, in fact, set up special microwave links between stock markets. So this guy here set up a microwave link between two of the stock markets in New York, the NYSE and the NASDAQ. In order to get an advantage over other people, whoever buys time on this guy's microwave transmitter here can get 100 microseconds from one place to the other. Right? So you can get there in 1/10 of a millisecond. And people who can do that maybe can make a trade. So that's what these guys are doing. Okay? They have all these little different pattern recognition devices. The problem is that as these machines are playing their little pattern recognition games, the original hedge fund machine was told, just kind of put stuff in the market as it's getting bought and sold. Well, the machine saw all these machines buying and selling, so it put more of the stock on the market, because people were buying and selling it. The market was moving. Of course, as it did that, these guys started trading even more. And so this guy dumped even more. And so in fact, over the course of a very small amount of time, this machine here tried to dump $4 billion worth of stock all at once into the stock market. This is a positive feedback loop, right? The hedge fund sells off stocks. This leads to the high-frequency trading algorithm, okay, selling between each other. This leads, in fact, to the hedge fund, the original computer, watching all of this and saying, oh, it's a good time to unload a little bit more. They set off essentially a cascade of buying and selling among each other. How does it end? Okay, so why are we not in the Great Depression? Basically, it went so bad that everybody left the system. You couldn't even buy things or sell things, and if you could get them for ridiculous prices. So, in fact, somebody hit the emergency brake. It triggered automatically, and everyone stopped all the trades. And then all those guys who thought they bought, Amazon for a penny or whatever, they were told no, undo. Yes.
So the guy who owned the first hedge fund didn't lose $4 billion.
I actually don't know how he came out in the end. He didn't do so well, okay? But he didn't crash the market. I don't actually know. So basically, at some point in time, they said, look, any trades made after this point, we're just going to cancel them all, right? So any trade made after, 238. So if you bought something at 239, okay, you don't owe the person for it, and they don't owe you the thing you bought.
Oh, you don't owe them back.
It's a total, they just said stop and undo. They just hit pause on the market.
So what happens to that money?
Which chunk of money?
Like
Oh, so like, okay, right. So it's like there's an $8 stock, right? For some reason, I could go in there and buy that stock for a penny. So, you know, it's you, right? So I give you a penny and you give me the stock because this is all computers. And then a little bit later, right, whoever owns you is like, wait a second. I'll take that stock back and here's your penny.
Okay.
And they were required to because that's kind of the rules of the game. Because markets, by the way, are all games. They're not real. So you can do this anytime. So these are signal cascades. This was a sort of two-step cascade. There's a signal that made me do Y. Y is a signal for someone else to do X. X, people trading makes me sell. Selling makes people trade. And this spirals out of control. Okay? Signal cascades can become, of course, more and more interesting. X may make me do Y. Y may make someone else do Z. Z may make someone else do X. Right? So you can get longer and longer cascades. Yes, right? These are the fundamental things where people produce something that other people misinterpret. They do something to the world. Other people look at the world, draw inferences about what's happening in the world, and make a decision on that basis. And if this loop ever closes, sometimes you just make a bad decision, but if your bad decision feeds back into the original thing, then all of a sudden you get either things going all the way up to the roof, or things all the way going down into the floor. So, at what point do things get really exciting? At what point do you get a flash crash, as opposed to just a kind of, you know, Apple has a little rally up and down? One way to think of it is, right, okay, there's a slight probability, there's a slight elevation that up is followed by up. There's N people in the market. Let's say that, you know, A of them buy, B of them sell, C of them hold. That's their natural inclination, okay? They get an up signal, and then maybe one additional person buys and one fewer person holds, right? Another signal, other people start changing their behavior in response, and of course, because an additional person bought here, it makes it more likely to get this one. So these are the decisions people are making, and these are the signals that they're using to drive those decisions. All right. So, if markets amass information, and sometimes when they amass information, things go horribly, horribly wrong, how or even why do we think it could go right? So this is kind of crazy, okay? Let's imagine we try to predict some event. Okay, I understand that Penn State won against Pitt, which is a university across the street. Let's imagine that there are, I don't know, N people, 100 people. Each of them has some idea about what's going to happen. Like, one person knows, oh, the quarterback was out drinking the night before. Another person knows that, you know, the ball has been deflated. They all have little bits of information that they get. And we'll call these private signals. These are things that only they know. They could sort of look in a box and see something. They have inside information. They have some really good theory about how sports works. Who knows, right? Not me. And let's imagine that all of these people, right, got a signal. That signal is noisy, but that signal gives them some information about whether or not, or what the outcome of this event is going to be. And let's just make it a kind of a reasonably strong signal, right? So if Penn State is indeed going to win, the chance that they got the plus signal the day before was 0.7. If, conversely, Pitt ends up winning, the chance that they got the plus signal the day before was only 0.2. So if a single person gets the plus signal, they say, well, my degree of belief that Penn State is going to win is 0.7. But now imagine that you got a whole bunch of people together, right? So let's say 27 people. Each of them gets a private signal. Then they get in a room together, and they all tell everybody else their private signal. And let's say they do that, and so 20 of these people got a plus, and 7 of them got a minus. That means 20 people got a signal that suggested to them that Penn State might win at this level, and then 7 got the opposite signal, the signal that Penn State will actually lose. Well, with 20 pluses and 7 minuses, and this set of probabilities here, that gives you almost perfect knowledge of the outcome of the game. So, you can work this out. We won't drag you through it, but you can work this out with the same methods you already have. So, how weak can the signals get? So let's imagine now, okay, that instead of having a, strong signal, so if I get this piece of information, it increases my belief that Penn State's going to win from 0.5 to 0.7. Let's imagine instead that it's really, really weak, okay? So if I get the plus signal, right, then it gives me basically almost no information. Right? If I thought that Penn State was 50-50 beforehand, I now think it's essentially 50-50 plus some tiny little number, epsilon. So what we want here is we're going to make epsilon as small as we can. By making epsilon small, what we're doing is saying that, look, you've got a really weak signal. You have almost no idea. You basically know nothing except just very slightly you have a chunk of data. And of course, this could be something silly like a football game, but it could also be something significant. It could be something significant like, for example, does this patient have cancer? Right? You have some machine. Cancer is very hard to understand. It's very hard to detect. You have some weak information off that object that tells you something. So E here is slightly larger. Let's say it's like 0.1 or 0.01. Say a whole bunch of people independently get that signal. How many people do you need until you can get, let's say, 80% certainty? Right? So before, when we had the strong signal, like a 0.7 signal, right, the chance of getting plus if Penn State's going to win is 0.7. It's pretty strong. Now the chance that you get plus if Penn State's going to win is almost a half, i.e. 50-50, just a slight elevation, right? How many people do you need to get together in a room to share all their private signals for Penn State for you to know the outcome of the game at 80%? It turns out if you set that level at E of 0.01, so you have essentially just a 1 percentage point advantage knowing your private signal. If you get everybody together in the room, and you assume that everybody's signal is independent, and you assume that everybody tells you the truth, okay? So these are your 3 conditions, right? Everyone's got to be in the room. They've got to share their information. They've got to tell the truth about their information, right? They can't, for example, like look at what everyone else is saying and copy them. Right? And the information they have can't just be a copy. That's his private information and I have mine, and they have to have come from different sources. That's equivalent to the idea that each coin toss is independent. If you do that, what I've plotted here is the case where epsilon is 0.1, and on the x-axis here I've plotted the number of people in the crowd. Right? So if there's just one person, right, that one person basically, if they get the signal plus, they have sort of a 51% to 49% belief in favor of Penn State. As you get more and more people together, they can assemble each of their little bits of secret information together to get an increasing confidence in this case, what would be a Penn State win. And to get 80% certainty, you only need about 1,500 people. Okay? So we're all a bunch of nerds. Right? We know very little about football, but if you got all of Carnegie Mellon together, each of them gave you a private signal on what they thought Penn State would do, and you averaged all those private signals together in the Bayesian fashion, just as you used, for example, the series of heads and tails to figure out what the bias in the coin was. If you use that basically somewhere around slightly larger than an incoming freshman class, you're going to get to 80%, and you can get to 95% with maybe just probably about twice as much. This is a magic trick, okay? The magic trick has turned everybody's private instinct, everybody's private tiny bit of data, it's amalgamated them together in a Bayesian fashion, and come out the other side with almost certain knowledge about an event. We're all really bad individually. We're all down here individually. But if we amalgamate all our data, we can learn a great deal. We all have the same coin. We each toss it privately. I toss it once. I get heads. I have no idea if it's biased. But if this entire room each tosses the coin independently, and we all share our data, we'll know exactly what the coin is. Exactly the same effect here. And all you need to do, if the signal is weak, is just get more and more people together. So this is the fundamental puzzle. Like, why are we not actually super predictors? Why don't we do this all the time? There's a lot of stuff that we don't know, but we have ideas about. I know a tiny little bit about this. Zach knows a tiny little bit about the same thing. If we get together, we can increase our information. If I can, I don't know, go on the internet and find another 1,000 people, why can't I get all of us to combine together and learn something that I didn't know before? There are two answers to this question. The first answer is actually we are, and so we'll do this on Wednesday. We'll show you an example of super prediction in action on Wednesday. You will be able, my experiments never work, but this one usually works. You will be able to produce a chunk of knowledge that neither of you has individually, and it's actually like not a ridiculous made-up coin-tossing thing. It's actually a real chunk of knowledge. So the first answer is actually like we are in many cases. It's one of the secrets underlying the market itself. If you think about it, what enables you to get coffee at Starbucks is that a lot of people have the right idea about a lot of things. Starbucks knows, for example, how to get its coffee. They know how much to pay for it, and they know how much to pay the people who work at Starbucks. If they don't pay enough for their coffee, what's going to happen? Well, in the current way it works, they won't be able to get coffee. But let's say they were able to underpay for the coffee. Well, that would mean the person shipping the coffee would, their tanker would run out of gas halfway there. The market is somehow able to balance all of these different ideas and to produce out the other side a remarkably effective system. And again, we'll see an example of that on Wednesday. Now, the other answer, of course, is that we're not. We're terrible at amassing information together. We're really bad at coming together to figure something out. For example, we're pretty bad at predicting the outcome of college football games. There's a couple of reasons. One is that there actually is a limited amount of information sitting around about the outcome of the Penn State-Pitt football game. There's not 1,500 independent pieces of information that each person gets individually and then could be reassembled in some gigantic room. There's not a lot of information there to be found. Penn State versus Pitt may be fundamentally unpredictable. That's the first thing. The second thing is actually kind of worse, which is that people don't actually do this the way they ought to do it, okay? And the problem is that we often set up our groups in a really inappropriate way, right? So in general, what do I do if I want to learn what you think? Well, I can get us all into a room and be like, okay, tell me your private signal. But usually what we do is we watch other people behave, right? And even if we're all in a room, I can't figure out what you know, I just have to listen to what you tell me. So I'm always watching you to figure out what you think, and you're always watching me to figure out what I think. And you're always watching, you can't peer into my brain, you have to listen. So sometimes we may know something, and we don't tell the truth. So here's an example. It's a very toy example. You have a box. In this box, it's either 2/3 red balls or 2/3 blue balls. Okay? So there's 1,000 balls in there. And it's either the case that the box has been set up so 2/3 of the balls are red or 2/3 of the balls are blue. Sorry, it's a boring example. It's a simple case, and then we'll get to the more interesting ones later. Here's what's going to happen. Each person's going to go up to the box, they're going to stick their hand in, they're going to look at the ball secretly, and then they're going to put the ball back in. Okay? So they get a private signal, just like in our Pitt versus Penn State story. Then what they're going to do is they're going to register their guess publicly. So then at the end, Zach's going to do this. He's going to put his hand here, and he's going to look at the ball, right, down, put it back in there. He's going to register his guess, and maybe Zach has seen a whole bunch of people before, so he doesn't just have his thing, but he also has what everyone has said before him. And at the end of this game, everyone who guessed correctly gets a prize. Right? This seems like a reasonably good way to set things up. I want you guys to figure out the truth. You each get a private signal. You tell everybody what the private signal is, and you get a prize if you get it right. And it's fine if everybody's right. That doesn't matter. Okay? It's not like if 10 people are right, then you get a smaller prize. You're not even in competition. So what happens? Well, okay. I'm going to put on the left-hand side the secret, on the right-hand side what you say. So the first person sticks his hand in there, and he pulls out a blue ball. So he then has to guess. He has to register his belief as to whether or not this box is 2/3 blue or 2/3 red. Well, he got a blue ball, and if he were a Bayesian, it's a pretty easy one to work out. Because he stuck his hand and got a blue ball, it's more likely that there are more blue balls, so he says, okay, blue. Okay. Then Zach comes along, he sticks his hand in, and oh, lo and behold, he pulls out a red ball. Okay. So what does Zach say? Well, Zach has seen a red ball, and he's also seen a blue ball. So there's sort of 50-50 here. He knows that there's at least one blue and there's at least one red in there. And so in fact he has no evidence either way. He knows that there's a blue and he knows that there's a red, so let's just say he guesses randomly. Okay? The next person, okay, maybe that next person gets a red ball. Now that next person has seen blue, red, and red, so that person guesses red. Okay? Next person sees blue. That person has seen blue, red, red, and a blue. Now it's even again, right? Let's imagine something slightly different happen, right? You have a private signal, okay? And in this case, right, the first person gets a blue, registers blue. The second person gets a blue and registers blue. Now the third person gets a red. This person knows three things. He knows that he's seen a red, but also that two other people have seen blues. He gets rewarded if he guesses correctly. His best guess is, in fact, that the box is dominated by blue, and so out the other side, he says blue. He lies about the signal that he's gotten because a lot of evidence all around him suggests that it's an incorrect signal. So he feeds an incorrect signal to the rest of the group, and now, of course, it's just doomed, right? Somebody else gets the red, they see three, okay. And at this point in time, the cascade takes off. Everybody in the room will have a good signal. If they all told the truth, we'd know the answer. But the way this game is set up, and in particular the way we've decided to reward people for being right, which seems like a reasonable thing to do, turns out to have a massively adverse effect. All right, on Wednesday, we will do the new Atlanta system. Please bring your laptops, okay? Zach and I will put you guys on a network and have you buy and sell and make money off of you. All right, very good.